Hi again, and welcome to another review session for Calculus 3208 for your final exam, brought to you as always by CDLI. In this session, we're well on now into Unit 7, our chapter on finding antiderivatives and integrals, and we're looking today at finding specific antiderivatives given initial conditions. So let's see what all that means now, if we can figure some things out here. All right, so we're going to talk about the concept of something called an IVP, or an initial value problem, okay? And then we're going to compute specific antiderivatives based on an initial value. Okay, so let's get into that. An initial value problem is basically, it's like telling you to find an antiderivative, but giving you a little bit more information. So if I had to find the antiderivative, let's say right here, of x squared, this is an example that we saw in several other sessions, but we get x cubed over 3 plus an arbitrary constant. Okay, so that's pretty straightforward. It becomes an initial value problem when not only do they tell you the function you need to antidifferentiate, but they give you some what we call initial condition. So we have an initial condition here, like f of 0 equals 1. Okay, so what that means is that after I find the antiderivative, the function that I end up with, when x is equal to 0, that function has a value of 1. So if I know that, I can fill those values into that function like we do here. So 1 is going to have to be equal to whatever that function gives me at 0. And that allows me to determine the specific value for my arbitrary constant. Okay? So then the specific value for my arbitrary constant here turns out to be 1. So my function f of x, it should actually say f of x, shouldn't it? So this should be f of x is x cubed over 3 plus 1. Okay? So that's kind of a neat way to go about that. And what that does, if we think about all the different possible solutions that we had, the ones that we talked about, this narrows it down so we know exactly which function we're dealing with. It's going to be y equals x cubed over 3 plus 1, which, according to the color, would be this graph right here. Okay? Alrighty, so that's the idea behind it. Let's see if we can solve some of these. The first one says, find f if f prime of x is 3x squared minus 2x, and f of 0 equals 5. Okay, so no big capital F's here, because they told us the function we have is called f prime. So what we're looking for, first of all, is f, given that that equation up there represents the function f prime. Okay, so let's see. This is going to be 3 times x cubed over 3 using our power rule minus 2x squared over 2 plus the arbitrary constant. And that reduces, so we get a little bit simpler here. It's just x cubed minus x squared plus that arbitrary constant again. Okay, now if f of 0 equals 5, that's information we can fill in here. It means that f of x equals 5 when x equals 0. And since both of those terms will be 0, that means that our arbitrary constant c is just equal to 5. So if we wanted to find f, we get what we call a particular solution. F of x will be equal to what we found it to be, x cubed minus x squared plus a constant, but now it's no longer arbitrary. We know what it has to be. It's 5. So there's the specific function, f of x. That's the antiderivative of this one, given that initial condition. This is actually, when you're solving an equation like this, or you're trying to find a function, f of x, given an equation that involves its derivative, this is sort of a very basic version of what we call a differential equation. And initial value problems are very common in the field of solving differential equations, but we're not really into doing DEs here, just finding some integrals, but this is sort of the precursor to that. So here we go. Find f of x, capital F, subject to the conditions that lowercase f, so its derivative is x root x, and f of 1 equals 1. Okay, so let's give that a whirl. So if lowercase f is this, let's write it in a friendlier form. So the derivative of 1, which is the lowercase, is going to be x to the power of, so this is exponent 1 plus a half, so 3 over 2 for the exponent. And since we have that, now we can find the antiderivative using our power rule. That's going to be x to the power of 5 over 2, divided by 5 over 2, or multiplied by 2/5, which is easier to write. And we have to, of course, add a constant, which is not terribly arbitrary anymore. We just don't know what it is yet. So, nice initial condition, f of 1 equals 1. So I'm going to say 1 is the value of f of x when x is equal to 1. all divided by 5 here, and then add c. So that tells me that 1 equals 2/5 plus c. So I subtract 2/5 from both sides of my equation, and it turns out that c would have to be 3/5. So then my function big F of x, which is the one we were after, is going to be 2 times x to the power of 5/2 divided by 5 plus c, which is 3/5. I guess we can try to write that in a more concise form. This could be 2 times the square root of x to the power of 5 plus 3 all over 5. And I guess if you wanted to simplify the square root of x to the power of 5, you could. So you could say 2x squared root x plus 3, and that's all over 5. Okay? So there's a good example for that stuff as well. Let's take a look at this one. Oh, look at this. It says determine an equation for f of x given this guy, which is its second derivative, and 2 initial conditions. One of the initial conditions tells us about the actual function, and one tells us about the first derivative. So we're going to have to use these in sequence. Our first step, though, to get to f of x is going to be to start to go from f double prime right here just to f prime first. So f prime of x will be the antiderivative of the second derivative, and that's going to be 8x to the power of 4 divided by 4 plus 5x. Okay? Plus our arbitrary constant. Can't forget that. Now, before we go any further and get to the actual function f, let's take note that we know some information about f prime, so we can get a very specific f prime here. So we're going to say that its value is 8 when x equals 1. So this is actually 2x to the power of 4 plus 5 times 1 plus c. So 8 is going to be equal to 7 plus c, so c has a value of 1. Okay, so there's good stuff to know about the first derivative. So we know from where we started, we've gotten at least this far. F prime of x is equal to 2x to the power of 4 plus 5x plus 1. Okay, so now we have to go after f of x, and we're going to end up using our second initial conditions for that one. So let's see, f of x is going to be equal to, now, power rule again, this gives us 2x to the power of 5 over 5 plus 5x squared over 2, and then plus another x, and another arbitrary constant. Let's give it a different name so we don't get confused. D. Alrighty. So we know that f of 0 equals 1. So if I let f of x equals 1, that means x would be 0. So this is 2/5 of 0 to the power of 5 plus 5/2 of 0 squared plus 0 plus d. So that tells us that d equals 1. Nice. So now that we have all that information, we can write our original function, f of x. And it's a polynomial that says 2/5 of x to the power of 5 plus 5/2 of x squared plus x plus our arbitrary constant, which turned out to be a 1. Okay? So there's a nice example of an initial value problem where we have to anti-differentiate twice and use 2 different initial conditions. Let's try the next one. Oh, and it's a test question, multiple choice. You know, multiple choice doesn't mean shorter necessarily. It just means you can't get partial marks sometimes, huh? Let's try this. So in this case, we've got to deal with a second derivative again. Okay? So they give us 2 initial conditions, but both of them are about f, nothing about f prime. So we're going to have to go all the way to f, 2 steps of anti-differentiation, before we can actually fill anything in here. So let's do that, I guess. F prime is going to be the integral of 12x minus 4. So that will be, let's see if we can do a little bit of this in our heads. Is that going to be 6x squared plus, oops, so what happens when I try to do it in my head, I write the wrong sign, minus 4x plus a first constant c. So notice that the derivative of 6x squared would be 12x. So I just divide it by 2 real quickly, okay? So then f, the original, is going to be, let's see, this will be 2 times x cubed, because its derivative would be 6x squared, minus 2x squared, whose derivative would be negative 4x. Now, c was a constant, so its antiderivative will be c times x. We don't know x yet. Plus, we have to add another constant because we've anti-differentiated again. Okay, so now we've got to start using our initial conditions. So let's use them one at a time. The first one says when x is 0, f of x has a value of 2. So I'm going to say 2 equals 2 times 0 cubed minus 2 times 0 squared plus c times 0 plus d, and that's a nice one because it tells us right away what the value of d is. So d has a value of 2, and now we know f of x a little more specifically. It's going to be 2x cubed minus 2x squared plus cx plus 2. Okay, so now we can use our other initial condition to help us find the value of c. So if f of 1 equals 1, I know that f of x has a value of 1 when x is equal to 1. So I'll fill that in here. And I've got 1 equals 2 minus 2 goes away, and that's going to be just c plus 2. So then c equals negative 1. So that means that my function f of x then has an equation f of x, that's an ugly f, equals 2x cubed minus 2x squared minus cx. Whoops, c we just found out was 1, so it's just minus x plus 2. And does that match any of our candidates? It does. A is the answer. Okay, good question. Like it. Your turn. Find f of x given this function and this initial condition. Yummy, a square root. Have fun with that. Okay, so here's the solution to the your turn question. Hopefully you're getting this done correctly and everybody's happy and hunky-dory. And let's just highlight a few of the key ideas of some things that we saw in this section. So for our purposes, an initial value problem requires us to find a specific antiderivative given an initial condition or a point on the curve y equals f of x. And that's what an initial condition really. It's a point on the curve of the original function that helps us figure out which one of those possibilities is the right one. So a basic method for solving IVPs is integrate the function to get y equals big F of x. Then repeat the step again if you have a higher order derivative. So let's say you start with a second derivative, you'd have to repeat that sometimes. Then substitute your initial condition in to find your constant. And repeat that again if you have to find two different constants. And write the equation for f using the specific value or values of the constants that you found. And that's basically it. That's IVPs in a nutshell. Hopefully you understand that, and hopefully it was helpful. And I'm really hoping your studying is going well. Ace that exam now, and if you have any questions, don't hesitate to put them up on D2L. All the best.